So we are going to use a few softwares today, but probably you already have all of them installed. In the file that I shared in the order confirmation when you purchase the Performant Fiber course, let me quickly check. Uh, what's on my cloud drive? It should be directly available. I don't know if you downloaded that zip file. It contains a couple of tools which we will need for, as this one is the software setup. Let me download it so that we it's here. Uh, yes, let me download it quickly. Here it is. Okay, here it is. You see that there are a bunch of tools here in this file. There is this Python script mesh sync, and then there are these 4 GHPY files. This is actually one single plugin, we could say. It's a tool that allows interoperability between Blender and Grasshopper. So basically, the mesh sync must be installed inside Blender, and this mesh sync GHPY files must be installed in Grasshopper. So the first thing that we are going to do, well, I'm going to show you. It's very simple, actually. When you open Blender, you already know that there is this edit preferences where you have these add-ons interface with all the list of the available add-ons. And you can install new add-ons. And you can install them by simply loading the py Python script. So in this case, you just press this button and go searching for the py file. In my case, of course, I already have it installed. You see, it's this one, Mesh Sync. You just install it, it will show up in this list, and then check this box, and it will be active. Okay? And we will see where this Mesh Sync plugin is located in the Blender interface. Okay? So just very easily, you just download the zip file and then install this py script mesh sync in Blender like this. Okay, so it's very easy. Just remember that when you install an add-on and you want it to be available, well, basically every time you reopen Blender, I have these auto-save preferences activated. If you don't, remember to save preference each time you change something in this Blender preferences interface. Also, by when you install or remove plugins. Perfect. Okay. And as for the GHPY, they are standard Grasshopper plugin. They just don't look like them because you see there is no Grasshopper green or yellow icon. They are just Grasshopper Python script. So it's basically the same. You just copy them inside Grasshopper special folders. So you go in Grasshopper, File, Special Folders, Components folder, but I have quite a few plugins installed, as you can tell also by my interface. These are DLL, and these are the GHPY, as you can see, for GHPY. And as always, when you install a plugin in Grasshopper, just remember to unblock the file. So you will see there is a message here saying that the file was downloaded from the internet, so it's blocked for security reasons. Okay, so unblock it, unblock the 4 file, of course, and then restart Rhino and Grasshopper, and you will see that there will be this. It's a very small plugin, actually. Just let me find it because, yeah, it's this one. See, Mesh Sync. So there are just 4 buttons here, 4 functions, and we will be using a couple of them. And this actually is a tool that it's basically inside Blender and inside Grasshopper. You just hit a button and it allows and helps creating some mesh exploitation structure, which is not only the polygons as we will see, but also, well, each mesh element, so vertices, edges, and so on. And it's going to be very useful for creating some nice, I would say some nice lattice-ish structure in order for have some interesting paths for the shortest walk. Okay, so that's it. You just have to install these two tools, one in Blender and one in Grasshopper, and you will be ready to go. And I also assume that you are working with Rhino 6 actually, so you know that with Rhino 6, Grasshopper comes embedded basically, and with Grasshopper also Kangaroo 2 comes embedded. So we are going to define some nice architectural mesh in Kangaroo and perform some analysis eventually in Millipede in order to derive some stress lines and understand how this stress line can be used in order to have some, let's say, change in the topology of the fibers. Okay, so this is what we're going to do today. It's going to be quite a large process, but in the end, I think we will come up with some nice result. So just please tell me when you're ready with these two small tools, and we will start. We will start with Kangaroo, of course. And also, I would like to know if you have some experience with Kangaroo. I suppose that you do, or at least you have played around. Is this a 0, Sagar, or is it a O?
Yeah, it's 0.
0. Okay. Okay, you made my day with this 0. Okay. Well, it's going to be some basic stuff with Kangaroo. If you have 0 experience with Kangaroo, of course there are other things in my page, especially about Kangaroo training. But if you go on YouTube, you
I
might.
went through your videos, which you had recommended before this workshop
Oh, okay,
regarding
perfect.
type simulation.
Perfect. Yeah, exactly. That's what I was going to show you. So yeah, that in that case, it's about textile simulation, but you will see now that those things are actually the same processors or the same workflow that you can use for some structural behavior. We will be working basically with a very simple definition in Grasshopper with Kangaroo in order to create some catenary pavilion or something like that. With some regular mesh topology, and then we will send that topology to Blender and see what we can do inside Blender to improve things a little. And also, we will also discuss an interesting thing that as we are basically shifting this fiber thing to some functional or structural behavior, I also want to show you what's the difference between working with a specific mesh topology or another mesh topology when it comes to structural behavior. So it's going to be interesting from an architectural point of view, and also from a design in general point of view. So sorry, Arish, I only know that Sagar is into architecture, but I don't know what's your background. Could you please spend 2 words and tell me what do you do in your life?
Hi, I work as an architect.
Oh, you too. Okay, so perfect. So you're interested too in this kind of stuff. So this is so good. I was afraid you were into another discipline. So well, okay. So let's talk architectural, right? So are you ready with these tools? Can we start?
Yes, please.
Yeah. Okay. So first of all, let's start with Kangaroo. Let's create this initial structure or mesh in general. We are going to create some catenary pavilion, but it can be whatever. Okay, so don't take this as the only workflow that you can create. Um, you might know that well, almost everything in architecture or in engineering, also civil engineering or building engineering, eh, you might know that all the 3D modeling and simulations cannot rely on surfaces. You know that Rhino is a surface modeler. So each time you create, for example, one single surface like this, you get a mathematical object which is perfectly smooth and continuous. So basically, if I should analyze or define the amount of points that we have inside this small surface, it will be infinite points along one direction, infinite points along the other direction, so infinite squared points inside the surface. And you cannot ask a computer to perform infinite calculation because it will take infinite times. And we want calculation to happen in a finite time. Okay? So that's why in all calculations based on some geometry, there is always some discretization going on. And this operation in a Rhino grasshopper means converting surfaces into meshes. So as Kangaroo is basically a physics simulation software, you must come up with a discrete system. You cannot work with smooth and continuous surfaces. So first thing that we're going to do, we are going to define some mesh. Of course, you can start with any body, any surface or polysurface in Rhino, import it into Grasshopper and convert it into a mesh. But there are some limitations. It is always better to control mesh topology so that kangaroo calculation and system behavior is a little more under control. For this, I would recommend, for example, that if you draw something weird in Rhino and you want to work with it, the first thing you might want to do, let's say that I want to B-rep join this, so I have this kind of strange solid. One thing that you shouldn't do is to set one B-rep, so here it is. You shouldn't use the mesh B-rep component. So when you want to convert some NURBS object into a mesh, don't use mesh B-rep, okay? Because this is a semi-automatic conversion from NURBS to mesh. So you have no control over the topology. You already have very few control over topology in Rhino Grasshopper, as we discussed yesterday. Mesh B-rep is the worst thing that you can do when converting a NURBS object into a mesh, okay? So don't ever use mesh B-rep, especially if you are into this kind of workflow. So what I'm going to do, I'm going to define some base mesh. And uh, we can, in this case, we can rely on Rhino because it has the necessary tool, which is a very stupid tool. If you go inside the mesh tools toolbar, you will see that one of the first comments that you have here on the left column is single mesh face. So we are going to create mesh faces one by one. Okay, with the limited potential that it has Rhino, but it's more than enough for us. So what I'm going to do, I'm going to create the first corner of polygon. Just remember that as, as for NURB surfaces, also mesh polygons have orientation. So we want these polygons, this mesh to be oriented upward with its positive normal. So just pick the vertices counterclockwise. It doesn't matter where you click this point, just pick 4 vertices. And once you have clicked the 4th point, just click enter. So you have one mesh polygon, okay? So always remember to circle counterclockwise. If you want to see what happens in this case, if I switch to shaded mode, you will see that the white face of this polygon is pointing upward. This is the positive Z space. And if I orbit and I take a look at the opposite face, you see that it comes up like orange. This is an adjustment, a settings that we have in Rhino. You can decide to see all negative faces with a specific color. This is not the default in Rhino, but if you want this kind of appearance, because I think it's useful to understand what's the orientation of surfaces and meshes, especially if you are going to somehow bring this object to reality with some manufacturing process. You must do this. You go into shaded mode, right click on perspective, go inside the display options tab. Rhino options pops up, and it's interesting to see that you are not in the document properties right now. You are in Rhino options. So the changes that you do right now will affect all the following files that you will open. And it also opens up directly in view display modes shaded. You see, we are here. And so we are tweaking the shaded display mode. And here, more or less at half the length of this page, you will find the backface settings. Now, by default, you will have use front face settings, okay? But if you switch to single color for all back faces, you can decide what is going to be the back face color for all the back faces in your models from now on. Now, don't try not to use, for example, some standard colors like the first one here, those who have names, because normally these colors are used by well, average users for visualization color, as visualization color. So you might be confused by the back faces. You wouldn't know if you're looking at the front face or back face. So use one of these colors here, which don't have a name, because they are seldom used by average users. Okay, and that's it. You hit OK, and then you will have this kind of behavior. And now, just to show you, if I create another single mesh face, but I go clockwise like this and hit Enter, you see that now I have the negative face of the back face pointing upward. Okay, so they are flipped. Now we want the back face to be down and we want the front face to be up. Okay, so remember to click 4 vertices counterclockwise. And then if you have the vertex snap activated, you can also create other single mesh faces, just picking the existing vertices, 1, 2, and then other 2 vertices and hit Enter. And you can go on with this. You can simply pick other, I don't know, 4 here and other 4 here at the top. It doesn't matter if they're actually square. The important thing is that they have 4 corners and 4 sides, and they have 2 coincident vertices with each other. They touch along one edge. Okay. Try not to create this other polygon here. For example, something like this, sharing 2 edges with other polygons. This is going to create some complexity. We don't want to run into problems right now. So what I'm going to do, I'm going to add another face here eventually, and another face here. Okay, so that's it. Don't make it too complex. The important thing is that all these polygons must have their back faces pointing downwards. Okay, so like this. Remember that we are creating 3D faces. Each one of these is a separate mesh, you see? So we can still select polygon by polygon. So in my case, for example, I have 6 meshes, separate meshes, even if they touch each other, but they are separated, okay? So what we are going to do, we are going to take this thing here and, well, basically join it, okay? We can do this in Rhino. We can try and do this in Rhino. Remember that Rhino is not the perfect mesh modeler, so maybe the result is not going to work. But let's give it a shot. So I'm going to select all these 6 polygons here. And if we go in Mesh Tools, you will see that, well, actually in Rhino there is one single join. It is Control J. So if you hit Control J, actually we have joined 6 meshes into one open mesh. Okay, so that's it. But this is not enough for a mesh. Meshes not only must be joined, they must be welded. So you see that there is this kind of welder here in the mesh toolbar, which is the weld mesh component. Okay. What it does is actually eliminate duplicated vertices along these adjacent faces. Okay, so imagine that here you have one vertex belonging to this polygon and another vertex belonging to the other polygon. So this weld eliminates these duplicate points and make this one single edge and not two overlapping edges. Okay, so you hit weld mesh. You see that the interior edges are basically becoming yellow. These are the interior edges that are detected because you have duplicated points corresponding to each endpoint of these edges, and you just click enter, and that's it. So if everything goes well perfectly, we now have one single continuous mesh. And what I want to do, I want to reference this mesh inside Grasshopper. So you might want to take a mesh container or mesh component, right click, set one mesh, and select this one. And now we have this mesh imported inside Grasshopper. Okay, now, I don't know if by chance, do you already have also installed Kangaroo 0099? You know that Kangaroo had a previous version which was called Kangaroo 0099. I don't know if you have it. It's not mandatory. I mean, we can also work without it. Nope. Okay. And so let's take another path. So what we must do here is basically increase the resolution of this mesh because we are working with this low amount of polygon. So, for example, just so that you have a quick understanding of what we are going to do, remember that we want to create a catenary pavilion or something like that. So we want this thing to become some kind of dome, okay? And we want this object to deform, for example, by maintaining these points anchored to the ground, okay? And so if these points are anchored to the ground and we apply some force pushing this object like upward, then what we expect is that this point here can rise up, reach to a certain height, and also this one, and also this one, you know. So all these points are going to displace upward. And so this is going to create this kind of shapes, you know. So this is going to increase like this is going to do something like this. You know, this is anchored, both are anchored, so this line is forced to stay on the ground. Also this line will stay on the ground, and also this line will stay on the ground, right? So this is the behavior that we are going to expect from this object. You know? Now, if we have this low amount of polygons, we only have one vertex capable of moving up. And so instead of having this kind of catenary structure here, we will only have this kind of linear thing. So we will have straight segments instead of arches. Okay. If you want to have to obtain some smoother structure, then you must increase the resolution of this mesh. Okay. Now, I was asking if you have Kangaroo 0099 installed because in that plugin there was this component here which is called quad divide. Okay. Now the quad divide is very easy. It only asks for how many division do you want in the U and V direction for each polygon. So, being 5, it means that each original polygon is now divided into 25 smaller polygons. Okay. Now, if you don't have this, we must create a workaround. And this is going to be, we will have to go back a little here inside Rhino. Okay, so what I'm going to do, I'm going to get rid of this mesh container. The old mesh here is, well, we will use it as a reference. What we are going to create is a 4-corner surface whose vertices are coincident with the vertices of the mesh. So what I'm going to do, I'm going to create one surface for each polygon, always counterclockwise, okay? So always the same rule. So we have to do this again and run through each of the 6 polygons that I have created, always counterclockwise. Fortunately, we are working with very simple meshes, so it's not a big deal, you know. And as now we have 6 surfaces, we still have the underlying mesh. You see that Rhino asks, what do you want to select, the surfaces or the mesh? We can also select the mesh. We no longer need it actually, and we get rid of it by deleting. Okay, so I have 6 meshes instead of 6 mesh polygons. 6 surfaces, sorry, instead of 6 mesh polygons. So now we can do the same, basically. I want to create a surface container here in Grasshopper. And now I want to select multiple surfaces, like 1, 2, 3, 4, 5, and 6. So they are all referenced here inside this surface container. And in Grasshopper, there is not only a mesh brep component, which is the one that we must avoid, well, as avoid it if you can. There is also another component which is called mesh surface. Of course, mesh surface only work with surfaces. So if you have a poly surface, you cannot use this one directly. But if you explode the poly surface and you have access to each and every face, that face would be a surface. So you can convert each poly surface face into a mesh. Now in this case, we have separated surfaces. So these are 6 surfaces. I will plug them here. Okay, and now you see that we have this grid of polygons inside our bigger polygons. Now I want to get rid of these surfaces here in Rhino, so I'm going to internalize data here in this surface container. So right-click, internalize data. So now we can also select these six surfaces and delete them. Also turn off the preview of this surface container, because we only want to concentrate on the mesh. In Grasshopper, normally mesh edges are invisible. So if you don't see this grid of polygons and you are in Grasshopper, just hit Control M. Control M is a toggle that allows viewing or hiding the mesh edges. Okay. And so finally, we have this higher resolution thing here. Now remember that we were working with 6 surfaces. So actually we got 6 meshes. Okay. We only need 1 mesh consisting of all these polygons here. So once we have these 6 meshes, each one having 36 vertices and 25 faces, we must do the same thing that we did in Rhino. Join these meshes and weld them. Now, if you go into the mesh toolbar and you go inside the utility group, you can mesh join, and you can also weld mesh. Okay, so there are 2 separate commands here. You just join these meshes and then take the weld mesh command, which is this one. Now see how the preview is getting more and more saturated red. This is because we have overlapping meshes, which are these 3 here. So each time you proceed to a new component, just turn off the preview of the previous ones, or else you will get some, apart from some strange visualization color, you won't be able to understand what's happening because you have everything visible at the same time. And as a result, we should have one single mesh with 198 vertices and 150 faces. Now this weld here should be also different from the join. You see that in this case, for example, when we join the meshes, we have vertices 216. After welding, we have only 198 because there are duplicated vertices in the joined mesh, and welding gets rid of those vertices. Okay, and so basically this result here is going to be our base mesh, and we are going to work in Kangaroo with this one. If you have this plugin installed, which is called Weaverbird, in the Weaverbird extract group, you will find a component which is called Weaverbird's join meshes and weld, which basically performs these 2 operations with one single component. So if you plug this here and you ask this component to also weld, because this is set to false by default, if you right click to this, invert, then it is also welding the mesh. And we should get the same result. But you see that in this case, there is some difference. So the result here has 198 vertices. But here we get 186 vertices. So that's what I was talking about. Rhino, grasshopper, which are the same thing, basically, they have a limited mesh modeling potential. When you have plugins that are meant to work with meshes, probably the result is going to be better. So if you have Weaverbird installed, you will find this join meshes and weld component. And if you use it, you see that we already have a better result because there are more duplicated vertices being eliminated. The weld mesh also work with an angle. So you can also tweak this value here and try and see if you get a better result. But this automatic component here normally works better. Now, there is a test that we can run on this mesh in order to understand if it was welded correctly. And it is using the mesh edges component. The mesh edges component is going to give us all the naked edges and interior edges of a mesh. So let's see what happens if I plug the weld mesh from Grasshopper. Okay. I have two separate outputs here. Okay, so if and they are lines because each mesh edge is a segment. Okay, so if I take a line container and I focus on naked edges, you see that I still have this naked edge here and this naked edge here. This is not correct because these should be interior edges, right? So this tells me that the standard mesh join and weld mesh procedure has failed in detecting these interior edges or collapsing these two vertices that we have here. Okay. While if I apply the same things to this mesh coming from Weaverbird join meshes and weld, you see that these two lines disappear. And so this workflow is better than the standard Rhino Grasshopper tools that we have. Okay, so we want a clear definition of the original mesh. If we still work with the weld mesh, mesh join and weld mesh workflow, we will have some error at some point in Kangaroo. Okay, so pay attention because actually the mesh must be correct. The mesh topology must be correct. Else you will have unwanted result in Kangaroo. So I'm going to leave this here like a note. I will group it and I will put here a warning or something like that, like a yellow group. So, well, not to you, sorry, but to you. So you will remember that there is something to pay attention to here. Okay. Okay, so let's move on. I could also take a mesh container, so we know that this mesh is the actually good one. Okay, and we have some kind of high resolution mesh. Remember that the resolution of this thing depends on the U count, B count of the mesh surface. So if I use, for example, don't exceed here the amount of polygons because else the calculation is going to be extremely heavy. So take actually it is 5 by 5. If you take a 5 slider, you can range up to 10. So if you do this, you see that we are already getting to a very high resolution thing. So we have 600 faces right now. I do recommend that you don't do this initially, just stick with the 5, because if a Grasshopper script work with a few geometry, it will work with whatever amount of geometry you want. The only difference is that you are going to stress the computer quite much, okay? And it might crash. And you don't want Grasshopper to crash when you are still working on the definition, okay? So this is going to be our mesh. What are we going to do with this mesh? Well, I told you Kangaroo is a physics simulation system. So basically it allows working with physical properties, so mainly material considerations on the system, and also physical laws. So, for example, gravity or pressure, wind, and whatever. So you see that Kangaroo interface is quite complex. There are a lot of groups of components, but let's come up with some schematic representation of this tab, because I repeat, it's quite complex. But in general, if you want to orient yourself inside this thing, you will see that there are many groups that are called goals. Okay, so goals are basically whatever actions you want to consider during Kangaroo simulation. And you will see that goals are normally subdivided into categories. And categories can be determined by the type of object or the type of geometry you want to apply some actions to. So for example, you will see that there is goals line, goals mesh, goals point, you know. So in that case, there are some particular actions that only work with some specific geometry type. Okay, and then there are some other groups that depends on the type of action actually. So you will find, for example, this group goals collisions. So whenever you want to work with collisions, that here are the commands for calculating or simulating collisions. And then there are the goals 6 degree of freedom. These allow to work with rigid objects, which is not what we're going to do today. And at the same time, you will find goals mesh, which are actions that work only on mesh objects, as well as goals point and so on. So this first part here, they are all goals, which means constraint, forces, actions in general. Then there is this main group. The main group is where the calculation is made. So it's pretty simple. And then there are these two blocks here. They are separated actually. One is called mesh and one is called utility. But in the end, they both contain utilities in general. Okay. Now in this mesh, you will find some mesh utility, of course. But in this utility, you will find some things that basically we already considered yesterday, just like, for example, remove duplicate lines, remove duplicate points. But there are also other uh, nice things that we are not going to see, but they are more general utilities. Okay, so we will be concentrating on this group, of course, because it is needed to let's say, implement the simulation, and on this one, because this is the one that calculates things in Kangaroo. And eventually, we will be using some utilities to help us create the system conditions. Okay, so it's going to be pretty simple workflow. Uh, in the end, we're only interested in creating some mesh here. What I'm going to do first, I'm going to tell Kangaroo that I want to work with this object here. And Kangaroo is a physics simulation system, but it only works with elastoplastic system. So we must define this body here as an elastic system. And then we will decide how strong it is, how stiff it is, in order to consider some material properties. Okay. So what type of object do we have here is a mesh. So if we go inside goals mesh, we will find a component which is called edge lengths. Now, if you think about elastic properties, you know that, for example, consider some spring, something like this. You know that basically during an elastic simulation, if you have these springs that actually measure something like L0, after applying a force to this mesh, to this spring, then you will have some deformation. So this spring will stretch a little and will reach a different length. So this is going to be length 1. And there will be a difference in length, which is called delta L. And now this is basically the deformation that you get when you apply this force. Okay, so this is the rough representation of the elastic equation. Okay, so deformation is equal to the force that you apply multiplied by this thing here. This thing here is the Young's modulus, which is a property, specific property, depending on only on the material. Okay, and so here, what we must define is actually what kind of deformation we want what kind of rest length or exercise length we want. So basically, in an elastic deformation or an elastic system, what matters is the length variation. Okay, so what this component does is calculate the edge lengths of a mesh. So we are going to simulate elastic deformation or plastic deformation according to the variation of the edge lengths of this mesh. Of course, if you stretch this thing here, each edge will be stretched individually. And so this is what this component does. And it only asks for a few things. Um, the mesh we want to work with, so it's going to be this one. What is the length factor? We are going to spend 2 words on this after the first simulation has ended. And what is the strength? Now, the strength is actually representing the material that we want to use. For now, we are going to leave it like this. It has already a scalar value, a preset, which is 1, as you can see, which has no physical meaning, actually. It is 1. It is not, I don't know, 1 Newton, I don't know, something like that, you know, some real physics unit. It's just a scalar value. And there is a reason for this. We will come to this later on. So basically, this component is already converting this mesh into an elastic net. Okay. Next step, we want to anchor this object to the ground in some specific points. And this is when mesh utility comes handy, because if we go here in the mesh group, you will find that there are, well, a bunch of components that might help in this case, but I'm going to focus on a simple one, which is mesh corners. Okay, so these mesh corners just takes a mesh and extracts the corner. Now, corner has a relative meaning because you see that it also depends on an angle. Remember that angles are defined in radians in Grasshopper. So if I take, for example, a slider between 0 and pi and plug it here, you see that 0 detects no angles. If I start to increase this, some corners start to appear. Okay, so pi is 3.14. This is more or less, let's say, a little less than 90 degrees. See, so that's why this sharp corner is being selected. And if I increase this value, other sharp corners should be selected like this. It doesn't matter if they are concave or convex corners. You see that they all get selected as we increase this value. If we increase it too much, we are going to come up with this. So this is basically considering a flat angle. And so also the vertices along the edges, as the inclination between two edges is basically 180 degrees, this becomes a corner, even if it is not a corner. Okay, so let's get rid of this and let's use the standard output that we get, but you know that you can use also more or less mesh corners if you want. So we have elastic properties, we have anchor points, actually. These are not actually anchor points for Kangaroo. These are only the vertices of a mesh, which are, well, simple points, okay? We must tell Kangaroo that we want to use these points as anchor points. And so we go, guess what, goals point, and we find an anchor. So let's take the anchor, let's plug the points to the point, and that's it, okay? Last thing that we need is, well, actually, this is the elastic properties of the system. This is the anchor points. Now we miss the force. So we want this thing to fall somehow. Now, of course, well, you are into architecture, so of course you know the work from Gaudí in Barcelona, and you know that Gaudí was actually working with this kind of stuff. But the only problem that guy had is that he only could work with well, Earth's natural gravity, you know, so its models were falling downward. But we are in a computer simulation, so we can program, for example, positive gravity, and so we can have this thing falling directly upward. Okay, so it's like putting the mirror below the Gaudi's model in order to see this, to see that model inverted. We can do this directly here. Okay, so what I'm going to create right now is a positive gravity force, and we want to apply this force to the whole mesh, of course. So we go once again in goals mesh and take vertex loads. So what this thing is going to do is going to apply the same load, which is going to be vertical, to all the vertices of our mesh. So we just plug, once again, the mesh to the mesh input. See, so we have this, and we define the strength. The strength by default is set to minus 0.1, which means that we have a negative, or well, negative Z orientation for this strength, which is quite normal because this is a load. But we want this to be positive because we want this mesh to fall upward. And so I will take here a slider like 0.1. So let's create the opposite of this. Oh, well, not 0.1, but 0.5. Okay. So something a little bit stronger, but positive between 0 and 1. So that's it, basically, because we already have all the things that we need for this simulation. It's going to be very simple, but it's going to be enough for creating some kind of nice catenary structure. So now what? We are going to go into the main group. In the main group, there are, well, you see several things that are named solver, okay? We're not going to go deep into this subject, but just so that you know, there are some solvers that only provide the final solution of your system, the final equilibrium state, and there are some solvers that show the whole process during calculation, so you can see how the system adapts to new conditions. Okay, we are going to work with the second one. So it's the bouncy solver. The bouncy solver is the, well, basically Kangaroo engine, you know, the component that performs calculations. So it has only one problem. It's not actually a problem, but some feature that you must be very well aware if you don't want Grasshopper to crash. It is already set to calculate whatever comes into goal objects. So the moment you plug something here, this thing starts to calculate. And you don't want that, because if you have a very complex system, this calculation can be so heavy that Grasshopper might hang or crash. And so the first thing you want to do is set this to false. But you see on, you see that by default is set to true. Just take a Boolean toggle and set it to false. So now it is paused. It can no longer calculate automatically unless you double click on false. And another thing that you might want to do is to place a button to reset this simulation. So in this case, just use a button and plug it into reset. So each time you want to reset the simulation, you just click here and you're resetting the simulation. So now the simulation is reset and false. It's stopped, basically. And you can start plugging the elastic force and shift the anchor points, shift the vertical load. When you work with Kangaroo, Kangaroo is generating its own preview of the system. So I do recommend that everything that's on the left, you can simply turn the preview off for everything. You are just concentrated on Kangaroo simulation. Okay, so everything is turned off by, like the preview is turned off, and we only concentrate on the result of this simulation. So you see that we only have this grid here. So what happens when we press this button and then release the simulation? So run the simulation by double clicking here. You see that this thing happens. Okay, so this is actually the equilibrium. Well, yeah, when Kangaroo says converged, it means that the simulation has stopped because it has reached the equilibrium state for this system according to the physical condition that we programmed here. So this elastic property, these particular anchor points, and this particular load are determining this kind of deformation here. And as this deformation only depends on gravity and elastic properties of the material, the shape of these arches here, they are all catenary curves. And so you know the principle. Basically, um, if we consider that each of these springs is actually has actually reached an orientation and a length based on load and elastic force, it means that it's only working with tension. And then it means that once you charge or load this structure with the load that you are considering, then this shape can easily bear that kind of load without changing shape. Okay, so that's what we are getting here right now. Um, so this is actually, you see that there is something strange happening. By the way, you see that, for example, if I go back and take this mesh component here and turn on the preview, you see that the mesh has a different representation in the preview. No, you see that it is actually some shaded object, while in the simulation we only get this kind of lines and dots. Okay, uh, this is because actually Kangaroo doesn't even care about the mesh itself. It only cares about springs, anchor points, and forces. Okay, so mesh objects are just an excuse in order to create a discrete system that allows the calculation to happen in a finite time. Okay, but it doesn't care about the mesh itself. But we do. We need the mesh. Okay, so we must recover this deformed aspect for our mesh. And the way to do this is to tell Kangaroo that we want the original mesh displayed after the simulation. And this happens in the main group. You will find the show component. So everything that is not relevant from a simulation point of view, you can pass it to the bouncy solver or to the solver via this show component. So I plug the original mesh inside the show component, which by the way can be turned off because it has no preview. And then I plug this together with the other goals in goal objects. So now you see that the deformed mesh is displayed. It is just the consequence of the deformation that we get for springs due to anchor point and loads. So it's just visualization, okay? But now, if you run the simulation, you will also see the mesh deforming accordingly, okay? But remember that the mesh doesn't interfere in the simulation. It's not necessary for the simulation. So now we have this thing here, this object, and let's see what we can do with this one. We have a bunch of parameters here. So we have the load. So if I decrease the load, of course, this object tends to fall less. Okay, so deformation is directly proportional to the force applied. This is the elastic equation, basically. So I increase the force, I get more deformation. Decrease the force, I get less deformation or no deformation at all. Okay, and so this allows to, let's say, simulate different load conditions. Now we are only working with a distributed load applied to the whole mesh. So all the vertices are actually receiving the same load, which is 0.13. We are also working with scalar values, okay? So this is not a physically correct simulation, but it's a good approximation of what would happen if we load this mesh with a uniform load applied to the whole body, okay? Then there are other parameters, like, for example, the length factor. Now, the length factor is like, well, you're architects, so the length factor is like applying some pre-stress to an elastic body. Okay, so say length factor is a multiplication factor. You know that if you multiply one number by 1, you will have the same number. But if you multiply this number by a multiplication factor that is smaller than 1, well, larger than 0 but smaller than 1, then you will have some reduction. And then if you multiply by a value which is higher than 1, then you will have an increasing of this value. Okay, so let's see what happens if I take a slider between 0.00 minor, smaller than 1, smaller than 2. Okay, so I want a slider between 0 and 2 with 2 decimal values, and whose value would be actually 1. Okay, and I plug it here. You see that nothing changes because this length factor is 1 by default. But if I decrease this value here, I am adding some pretension to this object, you see? And so if I create this kind of pretension, even if I apply a large value for this load, the deformation will be smaller because this object is more resistant because of this pretension, sorry, okay? If I, on the other hand, increase this, you see that the deformation becomes larger even with smaller value of the load that I am applying, okay? So this length factor allows to create some pre-stress condition, actually. This is very useful when you want to simulate some extremely elastic bodies, but in our case, it's basically irrelevant because normally architectural material, they don't have a length factor different than 1. The more interesting thing here is the strength of this edge length component, because this is actually a consideration, the property that allows to work with different materials. Now, just so that you know what are the pros and cons of this, of course, you can make a kangaroo work with the real physical properties, both for the material and the general system. But in order to do this, I'm going to only tell you the basics in case you want to further develop this kind of definition and create some real structure, okay? First of all, you must work in meters and not millimeters, okay? Well, at least if you work with the MPS system, so meters, kiloseconds, you must work with it with meters here, not millimeters. Okay, so draw your model in meters. If you draw your model in meters, you're half along the path because halfway along the path because the strength, the elastic strength of a body is actually defined by an equation. And the point is that this elastic strength is measured in Pascal. Well, actually, the elastic model is measured in Pascal. Actually, not in Pascal, in gigapascal. So it's a very, 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 very high number. Okay, and as the elastic strength depends on the Young modulus, which is measured in gigapascal, so it's billions like value. Then if you work with a real material, this strength here, instead of being 1, tends to be tens or hundreds of thousands, okay? So in order for you to know what's the equation behind this, I'm going to use just a scribble here. And the equation or actually we can create simply an expression. So you know, you will have it here available. So what I'm going to do, I'm going to create here an expression with E, which is the Young modulus, and I also need A, which is the cross-section or the area of the body that we want to simulate, and also I need the length of the body. And so the equation is going to be E multiplied by A divided by L. So it's very simple. This is the equation that we need to work with. Actually, if you go in my on my website, there should be already a post. Well, let me quickly find it because well, this is the recommended plugin that we already know, but I need it for getting directly to the blog section. I want to show you this post because it's important. You can also download the actual script that allows to work with the real physics magnitudes, or you know. So kangaroo tutorial. No. Let me go into the news category. Sorry, just a few seconds, so you will have the direct link for downloading this script. But I will leave you also the expression here. It's very simple, as you can see. It's just a simple expression. But in the script that you can download from my website, you also have a value list with already some preset Young modulus. Kangaroo digital parametric tiles. Let's go to the next page. Oh no, it's this real elastic strength. It's this one. So let me also copy the link. So I'm going to share this in the chat to everyone in the meeting. Okay, it's this. So if you go here, you would see, well, there is all the whole explanation of this thing. But here in the end, you can download the script which contains this cluster here, where you must provide the elastic modulus in gigapascal, which is something that you can retrieve on the internet. The area of the cross section of the spring, let's call it so, that you are considering, and what lines are being converted into springs. So remember to work in meters and square meters. We are not going to go into this, but if you want, you can download the script and give it a try. And if you have problems, you can simply get back to me for info. But anyway, if I'm not wrong, the elastic modulus for steel should be something like 210, something like that. But remember that you must consider the elastic modulus in gigapascal. Okay, so it's 210 gigapascal. It should be 210 billions of pascal. Okay, so let's provide these. And we will be working with an area measured in square meters. So let's say that these beams here are well, let's say square cross section with a side of 10 centimeters, for example, which means that the area is going to be 0.1 as a side, okay, multiplied by 0.1. So this value is going to be extremely low. And the length of this is measured in the, well, while approximating this to meters, it should be something around few meters. So let's say a variable value like 3 meters, okay? So if you do this, you will see that the result is going to be, well, something like, you know, in this case, it turns, well, actually, no, actually, it should be in Pascal, my bad. 1, 2, 3, 1, 2, 3, which is millions, and 1, 2, 3, which is giga. Okay, and so the result is going to be 7 multiplied by 10 at the 8th. Okay, so what happens if we try to use steel as a material for this edge length? Okay, the problem is that if we do this, okay, we can do this, of course. This strength becomes extremely high, and it becomes way stronger than the strength of the anchor point, which is only 10,000. So you see that the anchor point are no longer capable of anchoring this structure to the ground, you know, because these fibers here, these edges become too strong, and they just simply make this structure disconnect from the ground. There is also some deformation going on. If I move very close, you see that this thing is still adapting. Okay. If I recover some huge strength for this anchor point, they might go back to anchor this structure to the ground. But you see, for example, that this load here is not enough to make this structure fall up. So in this case, we must also work with real-world forces. So for example, let's say we want to apply, I don't know, 1,000 Newton to this, then it starts to make some effect. Even if you don't see it, if I go into the front viewport and let's take a look at this, you see that this thing is falling up very slowly. So the reason why normally we don't work with real world units, like for elastic strength or anchor point strength or load strength in this case, is because we don't want to waste hours waiting for this object to reach the final configuration. Okay, so that's the main reason. But you can do this. You can work with Kangaroo in a realistic way using real world units and forces. The only thing is that the simulation is going to become extremely slow. Okay, so I'm going to get back to our original. Well, you see what happens. For example, right now I'm applying 1,000 newtons to an elastic system which has only a strength or resistance of 1. Okay, so it gets totally stretched up. But I'm going to go back to 1, so this thing starts bouncing around, and I can recover the preview like here. So we are back to normal, more or less. Also, there is no longer the need of this high value for the anchor points. It's 10,000 is enough. So normally, the values that you have in strength for this Kangaroo component, They're all scalar values, but they are already preset to create some balance between the forces. So naturally, you want the anchor point to remain anchored in their original position. So that's why this component has the highest value for the strength, okay, with respect to the other. But then, finally, this is what we wanted to achieve, okay? Um, so where is this mesh? Actually, it is inside the output, uh, the O output from the bouncy solver. The problem is that, once you see converged, you can stop the simulation. The important thing is that you don't reset it. Okay, so you have the final configuration of this thing. So the output contains all kangaroo outputs. If we grab a panel here and we take a look at what we have here, we only have the mesh, which is this one. Then we have lines. And then in the end, we will find a bunch of null objects. Okay. Now, what are these things? Well, actually, the mesh is the data that comes from the show. Lines are actually the edges of our mesh. Remember that this component, even if it's applied to a mesh, it sets the elastic property by edge. So all the lines here are each mesh edge that you see here in the preview. And this is nice to know because you also have the information about the actual deformed length of this thing. So if you want to build this dome using, I don't know, rigid poles like wooden poles, you can simply rely on these values here in order to know how to cut them with the proper length. And you can also come up with a connection scheme and give names to each stick and so on. Okay, so this is something we're not going to do because we are interested in the mesh. And the null object are actually those actions or those goals who don't have a geometrical preview. So for example, the anchor points, these are constrained. So it's a very strong force applied to this point. There is no preview for a force, it's a vector, okay? So it results in a null object, as well as the vertex loads. So gravity is also a vector applied to each vertex of this mesh. And so you get all these null because there are all vectors applied to each of these vertices. Now, you might know that in Grasshopper, it's never a good idea to keep working with null objects. So we must get rid of them. And we want to focus on the mesh. So how do we isolate the mesh from this, let's say, non-homogeneous set of data? Well, the easiest thing that we can do is concentrate on the type of object that we are interested into. So mesh. If I grab a mesh container and plug the output to this thing here, the mesh container only understands one thing, mesh. When it receives something that is not a mesh, it does the same thing that was happening in the output. It generates a null. So if we had mesh and lines here in the output and then null objects, now we only have one mesh and all the rest is null object because this component doesn't understand lines. Okay, so even if this thing is red, it's good for us because now what we want to do is clean the tree by removing nulls. You see that remove nulls is set to true. So all the null objects inside this list or inside this tree are being striped out by this clean tree component. So you see that tree now contains only the resulting mesh. Question, clean tree, yes, exactly. Clean tree is more powerful than this, but in this moment we only want to get rid of null objects because we are only interested in this mesh. Okay, and now this mesh is our final thing. We already know that this mesh is a catenary pavilion or catenary structure, so we know that it can bear the load that we have programmed here. It is anchored to the ground in this point here. So we already know that this thing here has already some structural function. Okay. So we could also just follow this shape in order to create fibers. And if you do this, well, it's pretty easy. You already have a mesh structure. You can come up with the mesh edges right now. So mesh edges applied to this gives us this structure of lines. And you can also use this as the fiber paths. you only miss some wanted paths for the shortest walk. Okay, so this is something that is pretty similar to what we did yesterday. Also, if you want a more, let's say, a higher resolution for this, you must stop the simulation, go back to our initial mesh surface component, increase this thing here, and you will see that this thing here is actually a little more wobbling around, but because of these, the huge amount of springs that we have. And you can also tweak a little some values here in order to get to the desired shape. Remember that we are working with scalar values, so there is no particular meaning in this value. We are only focusing on the shape. And you can also use some easy slider for the strength. So an easy slider could be, for example, an 11 slider. Okay, this makes things, let's say, easier to control. Don't use huge amount for this strength. It has no meaning if you don't work with real life elastic properties. So this allows the springs to be more stiff, and so you will need more load, more power in order to deform this kind of thing. But finally, we have a higher resolution version of this object, which could be more interesting from a fiber system point of view. So let's wait for this to say converged. We have micro adjustment going on in this moment. We could also stop the simulation, but if you want to be more precise and have a real catenary structure, I recommend that you leave this running until it says converged. And then you stop the simulation. And then we have these mesh edges, which are all the edges from our mesh. Remember that we also need the vertices from this, so you might want to use a deconstruct mesh component. So we have the vertices and we have the meshes. Okay, and now what I want to do, I want to create a simple fiber system along this thing, and we need some wanted paths. Okay, so remember that we are going to use the shortest walk algorithm. So the curves that we want to use are all the edges, so both naked edges and interior edges. Remember that these curves here must be a list. So even if I'm confident that if I plug these two things here, I'm going to obtain one single list of lines, I always prefer to flatten this input in order to avoid any surprise. Okay, and what we miss here is the wanted path. So the wanted path along this thing, what could it be? Well, I don't know. I suppose something, or I want to play with something that in the top view, it could be something that runs from, let me grab a white paint, that goes from here to, for example, the center of this square here, okay? Or something like this, you know? It is actually just for playing around a little, you know, so created this kind of flow lines. We are not working with stress analysis right now. We just need some flow lines to run through this thing in order to have the fibers running in a precise direction. Actually, this is something that that is not that difficult to do this. Maybe we could also rely on this on the original surfaces that we have here, because we need the center point of these areas. You know, so basically we can calculate the area of the original polygons in order to have all these centroids here. See, and then we could find, for example, you see that let me turn off the preview of these edges and vertices. Okay, so these are the centroid of each polygon of the original mesh, you know, but this is the actual mesh. So we could also detect what's the deformed version of the vertex that lie at the center of each polygon. So during the deformation, this mesh is going to fall out, right? And so what I want is to detect what's the deformation exactly of this center point during the system deformation. So I would know what's the deformed version of this point here. So in order to do this, what I can do is something like this. So you have also another glimpse on kangaroo behavior. So we have these points. I'm going to calculate the closest point, starting from this centroid inside the whole set of vertices of this original mesh. So these are all the vertices of my mesh. You see that they are split into groups. That's because, well, probably I should work with the join meshes as well. So I already have one single mesh here. So I should have one single group. Yes, okay. And so if I do this, I get these points here. These points, the difference between the centroid and this point is that these points here lie on the mesh grid. So this point is going to be deformed during kangaroo simulation, not this one. Okay, and this is valid for all the centroid that you see here. So I want to see what happens to these vertices during the simulation. So if I take these closest points here and bring them inside the show component and turn off everything here, also turn off the original mesh. Now, here, I should also have in the output, you see that the last output here is a coordinates. These are points, right? So if I grab a point container and plug this here, I should get, yes, exactly. These are the deformed version of my original points, you see? So you can use the show component to monitor the deformation of each element that you have in your original system, okay? And so we finally could connect the anchor points to these points here in order to derive some wanted path, okay? So in order to do this, we have the deformed mesh, which is this coming up from the clean tree. We could use the same mesh corners that we have used before, even if the anchor points are not moving. But anyway, we have the same set of points. We also want to clean this tree in order to avoid all the null objects that we have in this set of data. And so we have, here we have 10 corners. Here we have 6 vertices here at their respective height. And then we must simply connect each corner to these points. Now, we can do, well, many things actually, but what I want to do, as I have 2 separate sets of points, instead of struggling creating a connection, I don't know, either by hand or by calculating closest point, I can also go in Heteroptera. Remember this wonderful plugin? Yesterday we focused on the incestuous network, but there is also one thing which is called non-incestuous network. So non-incestuous network allows to create connection between 2 separate sets of points. And we have one set of points here, 10 points, and another set of points here, 6 points. Now, points here must reach this this component in a tree flavor. So we need to send these 2 lists into 2 separate branches. Okay. So what I want to do, for example, is use an entwine, and I'm going to plug, for example, one list of points into one branch and one list of points into the other branch. So we have 2 sets, one with 10 points and one with 6 points, into one single data tree. And if I hide everything and do this, and then I will get to the question, sorry. If I do this, I need to define how many connections do I want per point and at up to what distance. Now, if I start defining the number of connections and I want to define also the search distance, I must refer to the model scale. So for example, let's say I want to reach a distance up to 50. You might see that we already start getting some connections, okay? If you want, you can also increase the amount of connections. Now it's set to 1, but if you set it to 2, you start to have more connections, okay? Like this. So we are starting to get some lines. I'm not let's say, absolutely interested in this thing. I just wanted to show you an alternative method. Of course, it needs some tweaking. But the important thing is that now we have a network of connections, which are all these lines here. And if we use them as wanted path, we are starting to get this kind of flow lines along the surface, or, well, the mesh, actually. Okay, they simply trace some path along the mesh, but these paths are determined by some wanted or desired group. Okay, so as you can see, we get this nice path here. Questions? I lost last 1 minute. I'm out of sync. Oh, yes. So can you tell me where you got lost exactly? What is your last?
After the closest point, before you use the show component.
Yeah. Okay. Here. Yeah. So look, what I was willing to do was considering some path for the shortest walk algorithm, connecting the corner points or the anchor points to the center of each of the polygons that we have in the original mesh.
Yeah, this part I understood. When
Okay.
we move to the moment you plugged in the show, this closest point output to the show component.
Yeah. So I calculate the closest point on the ground, which is a vertex from the original mesh. And then I want to monitor the deformation that happens to these points here. And so I plug them inside the show component together with the original mesh. So a kangaroo will track the deformation of the mesh object and also of these vertices here. And so if I do this, the output will also contain, if you remember, at first it contained the mesh, the lines, and then only null objects, which were the forces. But now at the end, you will find these 6 points, which are the 6 centroid from the original polygon, but now after the deformation. So you see that their z coordinate is now actually different from 0. Okay, and so I use the same method. I take a point container and a clean tree to obtain exactly the 6 points. And now, if I connect the mesh corners to these 6 points at their respective heights, I did it with the non-incestuous network, which is another tool from Heteroptera plugin. This is non-incestuous network. Yesterday, we were creating interconnections inside one single set of points. The non-incestuous network creates interconnections between separate sets of points. The only thing is that the point groups must come in as a data tree. And so I used an entwine in order to send one group to a branch and another group to the other branch. So we get this kind of simple data tree. It gets inside this, and you just tweak how many connections you want for each node and up to what distance you want these connections to be created. And then we have this kind of diagonal lines here. Maybe these lines here are useless because they run outside from the mesh, so we can decrease the distance, you see, and they tend to disappear. So now we have only this kind of internal connections, like diagonal, and they are useful for being considered like the wanted path from by the shortest walk algorithm, you see. And so we start to get this kind of flow lines along this structure. Now, this is not properly correct from a structural point of view, of course, because these are not stressed lines. This is just connecting the base of an arc to the upper point, more or less. So it's not properly correct. But nevertheless, it starts being something, you know. So this is the easiest thing that we can do, okay? But what if we start adding some volume to this thing? Because if we only work like this, we will always have some flat-ish set of fibers. But if you want to work with thickness, we can also have some a volume added to our base curves structure, okay? So let's see how we can do this. Of course, and as Sagar, you you were saying, I don't know if yesterday or 2 days ago. Yeah, 2 days ago maybe. Um, you can also rely on pufferfish, or you can also rely on any tool that allows creating a three-dimensional structure like a lattice structure. Okay, so the important thing is come up with uh, a complex structure, a complex set of curves or of segments actually, because this can only work with you see, with curves. Okay. Um, so it doesn't really matter the tool that you use. Just stick to the concept right now. There are also things that you can do. For example, using I don't remember if it was Lunchbox. It can create a three-dimensional, yeah, space trusses or something like that. But anyway, there are several things that you can do in order to create this kind of complex support structure for the fibers. Um, you could also, for example, use the same Weaverbird, for example, because Weaverbird has a component which is called Weaverbird's mesh thicken. So you could take the actual mesh that you get from Kangaroo and give some thickness to it. You see? Well, of course, this distance is actually measured in units, so I think it's too much. Let's take 1.00. So you can give thickness to this thing. Try to avoid self-intersection in the narrow curvature areas. So just tweak this value. But if you do this, you already start having a mesh with more edges. Okay, and you can also interconnect this internally. But you can use whatever method. Okay.
Just one question. Uh,
Uh,
I'm not seeing one of the components in my Dropter.
you don't see this thing here.
Yes.
Uh, this is very strange because, well, Heteroptera, as far as I know, it has no particular needs. You just install it and there is nothing more you have to do. But try and look for this component in the networks group inside the Heteroptera file, and it should be here.
Yeah, so it's surprising. It's not showing. It says internetwork. I think that's the name in my. It shows the same icon, but the name is internetwork.
Oh, maybe it might be that I am running an older version of this plugin. Maybe let me
I got
quickly,
it. It's
maybe
known as internet.
let me double check. Food for Rhino, because actually it might be. Okay, so uh, when you have this amount of plugins, it is also a job to keep them all updated. So maybe I'm running an older version, but let me see. 23 of June 2020 is the last update. So maybe yes. I suppose you are using the latest update, right? So
Yeah,
probably this is the reason, because in the picture I still see non-incestuous network, uh, but I do think that it's because my heteroptera is not updated. But if you recognize this icon, just use this component here. It should have the same inputs, by the way.
I got it. It's called internetwork, but it's the same. Yeah.
Yeah, perfect. Okay. So nice to know that I have to update my heteroptera. Thank you for that. Okay, so I think this is pretty clear what we are doing right now. So let's see what we can do when we go inside Blender with these things. Okay, so what I'm going to do, I'm going to take this mesh here. Oh no, by the way, let's take a step back. Because yes, we are going to go to move to Blender right now, but for two different reasons. Okay, one is for understanding how topology affects this kind of operation, because this is important also from the performant fibers point of view, and also in order to use Blender to create some nice, I would say in general, truss structure in order for the fiber to have somewhere to move along, something to move along. Okay, so instead of concentrating on the final output from Kangaroo, let's go back to our original mesh, which was this one. Okay, don't pay attention to the shortest word. Just concentrate on the original mesh.
I'm getting another error in the same component. It says solution exception, object reference not set to an instance of an object.
Of an object. Which component?
Same in my internet work.
Oh,
Yeah, this.
okay. But can you tell me what it's receiving right now?
It's, the input.
Yeah.
It says 00 n equals 11 and 01 n equals 7.
And these are points, right?
I followed the rest exactly the same way.
Okay, so
In Twine, output is 18 locally defined values, 00 n equals to x and 01 n equals to y. It seems the output, the result, is exactly the way it shows in your screen.
okay, do you have any additional branch here or in the tree, or you just eliminated the other branch that you don't need?
I have eliminated.
Okay. Look, can you please, I'm going to allow you to share screen. So now I will stop mine for a while and you can share yours so we can see what's happening.
Just a second.
Yeah.
I'm on a different computer, so I'll just connect from there. Can you guys hear me?
Yes, I can hear you.
Perfect. Just a second. Can you see the screen?
Yes. Oh, okay, I see. I see. Uh, hmm. Actually, when you get that kind of error, there is very few things that you can do because it's some internal error to this component. So this is something that it's very difficult to come up with a solution. Yeah, I see there is also an empty output. So it is simply not producing any result. No, sorry. Can you? I think they also changed the output. Can you please go hover with your mouse to the L output of the internetwork? Yeah, what it says network. These are the lines, so you can use them. Even if you have this kind of error, it should simply work. Can you click on shortcut work actually? So here are the paths, you see?
Okay, perfect.
So there is some error. I don't know. Eventually, you know what? Sometimes these interconnection things, like the incestors and non-incestors, they have problem when they get twice. They get the same point 2 times. So maybe this is what's happening. I don't know. I don't know. It's very difficult to interpret this kind of error. Because this is some internal error that we don't have access to understand what's happening. But anyway, the network in your case is at the bottom, so use
That's
those
working.
lines.
So yeah,
Yeah.
perfect.
Okay. So I'm going to stop your screen and
Done.
re-share mine. Done. Okay. So yeah, it's the network the important thing. Okay. Um, so what I was saying. Oh yeah, let's concentrate on the initial mesh. I want to bring this mesh inside Blender to do some topological operation and see how this can affect the system itself, and also the deformation itself. Okay, so in order to do this, well, the easiest thing that we can do, it's basically bake this mesh, which, by the way, is already joined and welded, so it's already a regular topology. And then we can right-click on the save icon, which is export selected object. I'm going to move this in our course folder, so 2020 and PFN, and this is going to be an OBJ format. Okay, we need just a mesh. So today is 20/08/22 or 23, sorry, and this is going to be our, I don't know, grasshopper to Blender start mesh. Okay, just to identify, to recognize what type of object we are exporting. Now, there is no particular reason to run in the options to check the options, because this is already a mesh object. Options only work when you convert some NURBS object into an OBJ. So I just click save, and then I just hit OK here. I don't need to tweak any parameter. Okay, so now we have a mesh object exported, and I'm going to hide this in Rhino, so we still have it available in case we need it. And I'm going in Blender. In Blender, I'm going to simply File, Import, and Wavefront OBJ. I'm going inside our work folder, and this is the Grasshopper Blender Start Mesh OBJ. Okay, so double click on it or import OBJ, and here we have it. Now, what I'm going to do right now is we are in object mode. Remember from the work that we have done in the first session. We are in object mode. If I go to edit mode, I have access to the actual topology of this thing. Okay, so I see all the vertices, all the squares, and everything. Okay, now my bad, I didn't lower the resolution. We are working with an extremely high resolution object, so tweaking the topology in this case is going to be somehow time consuming. Okay, so there is no way we can avoid this right now. But nevertheless, let's try to understand what we can do with this mesh in order to change the topology, which will also change the way this system behaves in Kangaroo simulation. So for example, I'm switching to wireframe mode, so Z wireframe, so everything is clearer. And I'm also going to see this thing from the top viewport. So if you have a numeric keyboard in your computer, just hit the 7 number, or else you can just click the Z icon here in this gizmo that you have on the top right corner. So just go into the top orthographic view if you want to follow my description right now, but it's not mandatory. So what I'm going to do, I'm going to show you what change we can do in this mesh object, topologically speaking. So for example, let's concentrate on this centered polygon that we have here, this one, because this is somehow a node in our mesh. You see, there is with respect to this thing, we have a lower polygon, right polygons, and upper polygons. If I consider this center point here, what we can do is, remember, we want to create independent loops of polygons inside this mesh. Okay, so let's consider this as a node point. If I run through this edge here, I get to this side. If I run through this edge, I get to this side here. And then if I run through this edge, I cannot reach the opposite edge, because else I would have some incomplete sections in my mesh. And so in this case, I prefer to turn right this way and get to this point. Now, think about this in terms of macro loops. So consider like if this was just one polygon, this was just one polygon, and so on. So if you consider the loops that will come from this division that I just outlined, you would have one loop flowing like this, and like this. You will have another loop flowing like this and reaching this point here, and another one flowing like this and like this. So three separate loops. They never interfere with each other, and they flow all along the mesh, covering it totally. Okay, so what we must do is create this kind of topological editing. How can we do this? Well, actually, if we consider the center vertex here and we want the topology or the loop to turn right at this point, we must take these 2 points here and create an edge with J, right? If we do this, we have this line here flowing like this. We must also get rid of the edges that we don't need. Okay, so first of all, let's add the edges, and then let's dissolve the edges that we don't need. On the other hand, we have this other loop that must turn in this direction. So we also need to create this edge here. And of course, this diagonal edge will propagate to this vertex, and this diagonal edge will propagate to the opposite vertex, right? So we need to alter the whole topology of this thing. Now let's see what happens if we try to do this. And also let's prepare the same thing here in this other vertex, because we will need, for example, this loop to turn like this. So we need another edge here. And we will need the loop coming from this direction, like this, to turn left. And so we also need this other direction of edges. Okay? So these are the center points, the center nodes for our loops. Let's see what happens in terms of propagation, because I need these also to be connected by diagonals if I want this to turn around this angle. But if I do this right now, I am respecting the actual resolution. This is impossible, because remember from 2 days ago that we also must dissolve edges. Why? Because we need quads. So for example, the moment I add this edge here, let's switch to edge selection. The moment I add this edge, I no longer have a quad here and here. I have triangles. So I need to recover and to reobtain quads in this area. And the quad containing this edge could be this quad here. And so I must get rid of this edge. But if I get rid of this edge, I would also have to get rid of this, and this, because I cannot simply delete one edge. I must delete one edge line. Okay? And so these edges here are going to be dissolved. So right click, dissolve edges. And now we have one quad, one quad, one quad, and so on. At the same time, I also have a triangle here and here. And so I must convert these into a quad. And so I must dissolve this edge. And if I dissolve this one, I must also dissolve this one. So right click, dissolve edges. So I have quad, 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 quad. I still have one triangle here. And so this is still a problem. And so in this case, I can dissolve this edge here, which means I must dissolve also all this line of edges. And so right click, dissolve edges. So now everything is back to quads. Okay, and I have this loop turning around this corner like this. So if I, for example, go switch to mesh to face selection and alt click on this edge here, you see that now I have a loop running like this. And on the other hand, if I alt click on this edge here, I have this loop running in this direction and turning around this corner. And here on this side, I have this loop that simply goes straight. You know, they simply pass along a side of this corner point. Now I have adjusted only this center point here. I still need to adjust things here because if I select this edge here, this loop runs through these other loops here, and this is not possible. So also this loop here must turn around this corner. So what do I have to do? I have to go back to vertex selection, take this, create a diagonal, and then start, and also on the other side, create a diagonal, and start dissolving edges. So which edges I'm going to dissolve? I need quads, so I will dissolve these with all its brother here, and these because it is also creating a triangle. And if I dissolve these, I must also dissolve these, and also all these edges here must be dissolved. Right click, dissolve edges. Once again, we are back to pure quads. Okay, so it's evident that this operation is also simplifying the topology because we are getting rid of many edges. Okay, but nevertheless, let's work on the main topology and then we will see what happens. Okay, so once again, I have to reach down to these corners here. So the operation is always the same. So vertex selection, add an edge, add an edge here, and then edge selection and start dissolving the triangle. So these and these must go away, these and these must go away, and everything that depends on them. So these, and all of these here. So right click, dissolve edges. We still miss a couple of edges. So let's go back to vertex selection. So these two J, these two J, and then edge selection, remove triangles, and all the edges that depends on these two and on these two here, like these all edges. Okay, now we are starting to have pure quads inside here. We only miss this one because we still have face selection, this loop running like this. It must turn around this corner. Okay, so once again, vertex selection, select these two, J, select these two, and J. Now, here we have some problem because dissolving these edges right now will bring to a topological thing, actually, topological problem. We should also work at the same time on the other thing. Just to double check, you see that now if I select this, this loop runs on the left of this corner, but this is turning, turning, and this is stopping because it has triangles. Okay, so we must convert also this thing in quads. And in order to do this, we should dissolve these two here. So if I right click and dissolve these edges, I have this. But this is a problem because these are not quads. Now these are pentagons. They have 5 edges. And also this one, it has 5 edges. Okay, so this is a problem because if I take this line of edges, right click and dissolve it, I start losing something along this edge. And also, if I select all this line of edges and dissolve it, I am starting to lose the original corner point. This is inevitable, okay? So this topological editing that we are doing is also deforming a little the general aspect of the mesh. While all this editing inside this area didn't change the outline of the mesh, dissolving the edges that converge into a vertex or a corner is actually changing the topology, the shape. So if I control Z, you see that now we have a vertex here. If I dissolve this edge line here, you see that this vertex disappears. Okay, so we are slightly changing the shape of this object. And the same thing happens if I dissolve all this line of edges, right click, dissolve edges. Now we will have also to dissolve things that happens here. But nevertheless, if we do this, we now get this kind of loops that always turn around the corner of this inner polygon. Okay, something like this. And now we have to concentrate on what happens here because we want also them to turn in this direction, okay, to the left. So vertex selection, we already have some triangles going on here. So let's start dissolving edges. So I have this triangle, this triangle. Remember that we want to turn left. So the edge that I want to dissolve is this with this here and this also. So right click, dissolve edges. So this is already turning left. And if you take a look here at face selection, you see that this loop here now runs like this, and reaches this side. So if I alt click here, I have this loop of polygons. Okay, and I have to do the same with the rest in this orientation, this diagonal right now. So back to vertex selection, take this, J. We can also directly add all the diagonals. So we can simply do something like this. And we also need on the other side something like this. So we can only just concentrate on the edge dissolve right now. So select edges, and I need this to turn left again. So I remove all these edges here, like right click, dissolve edges, and remove all these edges here. Right click, dissolve edges, all of these, dissolve edges, and these two here, dissolve edges. So all these loops right now are turning left correctly. And then I concentrate on this, as it's the same basically. So remove this and this. If I remove this, remember, I must also remove all of these things here and all of these things here. So dissolve edges. And then these two here, dissolve edges, these two here, dissolve edges, and these two here, and dissolve edges, and also this, because here we have a pentagon. Okay, so right click and dissolve edges. So this is the final topology that we can consider for this for our mesh. So you see that if you go into face selection and now you click this, for example, or this, alt click, you see that all these loops just run separately. They cover all the mesh and they run separately. See? And so this topology is way more, let's say, efficient than the previous one. Of course, Kangaroo doesn't care about this, okay? But if we want to use this topology in order to perform some kind of fiber system population, then this might be useful, because if we have this, remember what we did 2 days ago, we can create some, I don't know, flowing patterns along these lines, okay? Now, actually, this topological edit here, by working with loops, is only necessary if you are going to work with that kind of workflow. So if you want to apply some module along this mesh with some orientation, then you must come up with this kind of loops optimized topology. But if you want to work for creating some kind of truss system, just as a support for our fibers, then this is not strictly necessary. Okay, so this topological edit, you must do this only if you want to have separate loops that help creating some kind of striped pattern along this mesh. Okay, and once you have this, you might want to send it back to Kangaroo, and eventually, I don't know, see how it behaves in a kangaroo simulation. Now, the problem with this is that we have basically dissolved many edges, so we have very large polygons in these areas and very small polygons in the remaining part. And in kangaroo, this means that you have very large springs and very short springs in different areas. And this means that this area can deform more smoothly, and this is a very low resolution part. So what I would do in this case would be to decrease the resolution of this mesh globally in order to obtain some low resolution aspect. So for example, I would say let's alt click, let's go into edit mode. Let's go into edge selection. If you alt click on one edge in one direction, you select the whole loop. So if you want, for example, this extension for this, let's say, polygons here, then you can select all of these vertical loop of edges and dissolve them. So you see that now we have somehow more or less the same resolution for this in this part of the mesh. And do the same here, for example. So alt click, shift alt, shift alt, shift alt, and so on, and dissolve them. And also here you can remember that this is the separation between two polygons. So I'm going to select all of these, and these, and these. Skip this one and select all the rest here. These and like this, so dissolve edges. So now we have a more uniform topology for this, well, at least polygon size for this thing. And we can, for example, if you want to work with this, you can also apply some subdivision surface algorithm and start getting some nice topology. Remember that, as we saw 2 days ago, this is actually not changing the loop conditions. Okay, this is only creating a higher resolution version of the same topology. If you want it with some smoothing, then you use Catmull-Clark. If you want it simple, then just pick the simple. But the loops are always turning around these corners here and this corner here. Okay, but if you want to work with Catmull-Clark, it's going to be even more interesting. Okay, so once you have this, you can re-export this object as an OBJ, re-import it in Rhino, and we'll see how Kangaroo works with this kind of thing. Okay,